Welcome to this week's Pass the FE Exam video. In this week's episode, we will be breaking down the equilibrium of rigid bodies, zooming in on how to figure out support reactions at a roller. We'll take you through each step to make it easy to understand and apply in solving support forces in complicated structures. This problem was created and solved by mechatronical engineer Shante Thunderspey, and is brought to you by PPI, a leader in engineering exam prep for the FE and PE exams since 1975.
PPI provides expert prep courses and study resources designed to help you pass the FE exam the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. With study guides, practice exams, and more, the PPI Learning Hub offers digital practice and review that you can take with you anywhere you have a device so that you can prepare during the times most convenient for you. Check out PPI today at ppi2pass.com to see all the options available for FE exam prep. Let's dive in.
In this question, we are given a diagram showing two structures connected and supported by a series of pins and rollers at A, B, C, and D. A concentrated 6 kN load acts on this structure, causing reactions at these supports. And this question specifically asks us to determine the support reaction at roller D. We are given 4 possible correct answers ranging from A to D. Let's dive right in. We can start to evaluate our problem by drawing free body diagrams of the individual elements within the system. First off, we can isolate the small beam resting on our V-shaped structure, and we can include the 2 known forces acting on it. Specifically that 6 kN force at 3 meters from the left, and the 2 kN moment acting on its far right end. After this, we need to include the reaction forces acting on the beam due to the roller and pin that supports it, and we label them FB and FC. I have chosen the positive direction for these forces as upwards so that they balance the downward 6 kN force on the beam, but you could have also chosen them to act downwards. What's important is that you stay consistent in your directions when drawing the free body diagrams. As you can see, these forces create a compressive force on the beam, meaning they must have the same effect on the second element. So in this free body diagram, we choose the positive direction to be downwards. We need to make sure that we draw these forces as compressive in both diagrams to ensure we link the two correctly. Following this, we can add support reaction FAY. And once again, I have chosen it to act as upwards so that it can balance with forces FB and FC. What's important here is that we don't forget force FAX. Since we have another force acting in the X direction, force FD, we know that the pin support at A must balance this force. This is in contrast with what we saw in our first free body diagram. Since we had no other forces acting in the X direction, there was no need for a reaction force in the X direction at pin C. And finally, we can add the star of the show, force FD. In this case, note that FD can only act in the left direction, since the beam is supported by a roller at this location. After completing these diagrams, we can start working on solving some of our unknown forces. And since the second free body diagram does not contain any known forces whatsoever, we know the first element will provide a better starting point. We can start off by taking a moment balance about point C, since doing so means we'll end up with only one unknown, force FB. By taking anti-clockwise as the positive direction, we have the 6 kN force working in at a distance of 6 meters in the positive direction. We have our 2 kN moment about point C in the positive direction. And lastly, we have our unknown force FB working in at a distance of 9 meters from point C. It is important to note, however, that this moment is applied in a clockwise direction. So according to our convention, this moment must be subtracted from our equation. Another thing to take note of is that force FC is left out of this equation completely. Since this force acts in at point C, the distance to the force is 0, resulting in a negligible moment about this point. The sum of these moments all equals 0, allowing us to solve for Fb, and we find that it is equal to 4.222 kilonewton. We can now do a force balance in the y direction to find force Fc as the only unknown. By taking upwards as the positive direction, we find that forces Fb and Fc act in the positive direction, while the known 6 kilonewton force acts in the negative direction, meaning we need to subtract it from our equation. The sum of these forces all equals 0, and by substituting force Fb as 4.222 kilonewton, we find force Fc to be equal to 1.778 kilonewton. We have now solved for all the unknown forces in our first free body diagram, meaning we can move on to the next element. Looking at our second free body diagram, you might be tempted to start solving for force Fay, since this is the only unknown force in the y direction. But upon closer inspection, we see that force Fd can be solved for directly by immediately taking a moment balance about point A. In doing so, we eliminate the need to compute the reaction forces at A. By taking anti-clockwise as our positive direction again, forces Fb and Fc cause negative moments about point A, and they work in at distances of 5 meters and 7 meters respectively. Our unknown force Fd causes an anti-clockwise moment about point A, and it works in at a perpendicular distance of 12 meters. This allows us to write our final equation as negative force Fb times 5 negative force Fc times 12 plus force Fd times 12 is equal to 0. By substituting forces Fb and Fc, we finally find that the reaction force Fd is equal to 3.537 kilonewton. And that completes our problem. By browsing the options given to us, we can see that the final answer is equal to B. I want to conclude this problem by offering some pointers. When starting a problem like this, be mindful during the construction of your free body diagrams and take special note of forces shared between elements. If you chose a reaction force as compressive on one element, you need to make sure the force is indicated as compressive on the second element. Secondly, ensure that you correctly identify the support types that you are working with. Thirdly, apply the equations of equilibrium correctly, paying attention to signs and units. I recommend choosing a convention for your positive directions and sticking to it. For example, in this question we chose upwards and anti-clockwise as positive. By sticking to the same convention throughout your practice, you might find that you make less errors in this regard. Finally, and as always, hone your skills by practicing with different loading and beam configurations so that you can become confident in your ability.
I hope you found this week's video helpful. In upcoming videos, we will answer more of your FE exam questions and run through more practice problems. Pass the FE exam will publish videos weekly, so please be sure to click that subscribe button as you'll get expert tips and tricks, including practice problem solutions like this one, weekly to ensure that you pass the FE exam. I'll see you next week on Pass the FE exam.